we talk about some definitions and examples, and especially we present invariants to be able to talk about the classification, the panorama of the classification of fusion and modular categories. So we talk more in detail about modular data, the classification by rank that I said it's on archive up to rank 11, but coming soon rank 12. Then I mentioned that if you restrict a little bit more, meaning that now we have that all the dimensions of all objects in the category are integers. And again, this means that our category is related to quasi-Hopf algebras. In that case, there is results of classification up to rank 13. And if you go even further and you restrict that the dimension of your category is an integer, but also some restrictions on it, like divisibility odd or not divisible by 4, we got more results, so up to higher rank. And that gives us some ideas about how to tackle this conjecture, the weakly integral conjecture from 2009. So remember, this conjecture was, if you have a fusion category that is weakly integral, meaning that the dimension is an integer, then it's weakly group theoretical. Weakly group theoretical was just that the center of this category is Brady equivalent to the center of any potent category, which I will review the definition in a minute. And then this, as I mentioned yesterday, we also conjecture later that Fay-Thompson for fusion categories should work. I mean, it's a conjecture, but so this for then let's see. The conjecture is stated for all, but probably could be operated to 4 doesn't divide. Is sorry, over. And if this conjecture is true, then it will follow that it's weakly group theoretical for these families. So it will be a partial proof or a proof for certain families of the other conjecture. So this will give more evidence if it's true. And I just wanted to remind the definition of nilpotent, because I think the definition I gave, there are equivalent definitions, but this one is more clear and also gives some hints on things. So if you start with a fusion category, you can always have this nice subcategory that I didn't want to define yesterday, but I think it's actually easier and it might pop out later. What is this subcategory? You take every simple object and you tensor it with its dual. And now you tensor generate with this. So it's the category generated by these objects. So you take this tensor product, you look which simples you get in here, and you start getting a tensor category out of it. This is the subcategory of the original category, and it's called the adjoint, and it's important, and I might mention later more. And if you notice, this subcategory only depends on the fusion rules of the category. It's not taking in account the associativity at any point. And now we can define a sequence, so this might remind you more of nilpotency in a usual way. So we can define the sequence in the following way. C0 will be C, C1 will be the adjoint, and now I will take adjoint of the adjoint of the adjoint of the adjoint. If there exists n such that Cn is vec, then C is nilpotent. Of nilpotency degree n, if that's the first time that vec appears. Basically, the thing that could happen is that sometimes you get stuck. You get to the adjoint, and you take the adjoint, and it's the same thing, so you cannot keep going. So some things is so for example, if I start with the category rep G, C is nilpotent if and only if the group is nilpotent. And the same happens for solvability, that I gave the definition that it's Morita equivalent to cyclic nilpotent. But, for example, if we take vec G omega, one of our favorite examples, I told you the simples were one-dimensional vector spaces concentrated in degree G, so I will call them like this. And I said actually that all of these are invertible, meaning that if I tensor with the dual, I just get isomorphic to the identity, which I call delta E. So if you do this, here the only simple you have is 1. So when you do this and you look who is the adjoint of this, it's just generated by 1. So we get back. So these are the ones that are nilpotent categories. So if you see, this was true for any group. If you want to know when this category is solvable, it's if and only if the group is solvable. So something that happens is that for groups, nilpotent implies solvability, but for fusion categories, it doesn't. Now, if we add the restriction that the category is braided, which I don't have here in general, it will also be true that nilpotent implies solvable. So it's a little bit different, but I wanted to mention, and one important thing is nilpotent, because of this definition, only depends on the fusion rules. It doesn't care about associativity. We don't know if that's true for solvability. Some people was thinking about this question for a while, and there are papers by Sonia Natalia addressing some cases of that. So it's an open question, knowing if it only depends on that, because it's defined in terms of Morita equivalence, which in principle we have it in mind. But for example, this question here, this part here, these things here only depend on fusion rules, even if in principle, I mean, we want to prove something that it's not only dependent on fusion rules. So I just wanted to make this because I got some questions and I thought maybe the other definition I gave is less transparent, so I wanted to mention. So maybe one idea to convey yesterday was, okay, classifying fusion categories is really, really hard. That's why we don't even know much, even by rank, it's rank 2 or 3, depending how you want to think. But even modular categories in which we have a lot of more structure and things to play around, there's anti-matrix, all these number theoretical tools, SL2 representations, still very hard and it's still wide open. So what we did yesterday, basically, in my mind, is we tried to organize things that we have in some ways. That's what we were doing with classification. We have a lot of things, we wanted to organize it in certain ways, and we were classifying for that. Today I will focus more on the other part that I was mentioning, getting new things from known ones, so constructions. So I wanted to list a couple of constructions. Some of these are for modular categories. I will write a lot of constructions, and then we will go more in details in some of them. And some of these constructions are for modular categories, but some are more general. So we will try to say that while we talk. So maybe the first one, maybe the most friendly one, it's the linear product. If I start with 2 fusion categories or modular categories, I can take the linear product, and I will get the same kind of output, fusion or modular, depending what I started with. So in this simple case, describing the linear product is basically easy. It's a direct product idea, what we're having. So the simples in this category will be just the tensor product of the simples of this and this category. And all the other things will be also product. All the constraints will be getting by the product. So we are doing this kind of direct thing. When it's not semi-simple, things get a little bit harder to describe, but we will be doing that. So this is kind of a easy, in some sense, construction that we have, but we have it in hand. So Dreamfeld Center, which yesterday I mentioned. Here, if I start with a pivotal fusion category, I will end with a modular category. If I just start with fusion, I will end with a non-degenerate bracket. The pivotal is giving me the ribbon structure, the tracing things. Maybe I wanted to say something about this. Yeah, this construction is also nice because I don't know if you remember yesterday when I was talking about the classification result for, or the characterization, maybe result for fusion categories that were modular with dimension congruent to 2 mod 4. What we did was to decompose it as a linear product of things. So a lot of the times you want to see if you can factorize your category in simpler ones. It's make it easier to understand if you can. Sometimes you cannot. So this Dreamfeld Center, I should say spherical. fusion category. This Greenfeld center, the idea is that usually when you think in centers for groups or something, it's something smaller. This category is bigger. And in principle, this will not be inside here. There will be from here a forgetful functor to this one, but not the other way. When this one is braided, it sits inside this one. So what is this one, which I will not write in details, but it's this nice machine to do this, and I told you what happens is Hoff algebra, for example. But the idea is that what we do is we equate our objects in these categories with something that it's a half braiding. So in Jenny's talk, we have the braiding. Here we want half braiding. So we want our fixed object that I start with to be equipped with a family of maps that lets this object commute with any other object in the category. Commute in the sense that you can switch the tensor product. So the family of map is telling you that, but they are half braiding because for the braiding, remember, we had to satisfy two hexagons that were basically telling us how I could write something like this in terms of CXY and CXZ and associativities, and also in the other side, I could take the tensor product. But here, the object is fixed, so I only can put the tensor product in one side, because these are the ones that I'm allowing to change. That's why I only have one hexagon, and that's why we call it a half braiding. And you can equip this with a tensor product and all this using the original structure. So that's the Greenfeld center. Something nice, for example, I told you that the rank goes crazy. We don't have a bound, but we know the dimension. The dimension is the square of the dimension of the other category. And it's a very useful construction because it gives you a modular fusion category. In principle, I will not say much more about the Greenfeld center, but it's useful. Then there is this construction called modularization that was independently described by Müller and Bruyère. And later I will say one maybe more general case, but if I start with a braided fusion category, I told you that we can measure how far we are from being non-degenerate by looking at this subcategory that was important, the Müller center or the symmetric center. I mean, it measures how far you are from being symmetric or modular, because these were the, or non-degenerate, the string cases. So what I will do is I will try to fix, maybe here I will say B for braided. So what I will try to do is fix that this is failing. I mean, if it's back, we are fine, we're non-degenerate, but it could fail to be back. So we will try to fix that and get a non-degenerate fusion category. But I cannot do it always. I told you this is symmetric. So by the delineate theorem that we stated yesterday, we know how they look. They always are rep G set. We will not always be able to fix it in principle with this method, but if this is one of these rep G, when set is equal to 1, so just representations of a group with a flip. In this case, which we call Tanakian, that is super Tanakian because the set is giving me this sign, this grading. In this case, we can get a non-degenerate braided fusion category in a way that, I mean, we call it modularization in this case, but can be done a little bit more general, and it's called the dequirantization. And what is this category? What we are doing is we have this subcategory, and then with this we can construct a commutative algebra in my category. Which algebra? The algebra of functions of this group. So now this will be a commutative category in my commutative algebra in my category, and then I can consider the category of modules for that algebra. That is what we are doing here, taking modules over this commutative algebra. So this Tanakian is important because it gives me the commutativity, and that tells me that this will be fusion again. If I have super, it will not be fusion. But you can do something else in that other case. Maybe I will not. So maybe in that direction, this was to get something like this, but we can do Okay, I wanted to say two things, but I will say one first. And then I will say the other one. So if I have a G action of a group in my category, so this is a categorical action. So basically, what I will do is I will look at my group as a category, and I will have a tensor functor to the tensor autoequivalence of C. So what this is telling me that each time I have G, I get rho sub G that will be a functor from C to C, that will be an autoequivalence, and that will be a tensor functor. So behaves nicely with the tensor product in C. But moreover, all these rho G's also carry a tensor functor structure. So there is a lot of unpackaging to do in that line, which we will not do now. But when you have something acting on something else, something that you could do is take fixed points of this action. And that's what this equivalentization does. So associated to this, there is this C to the G, let's say, that it's the equivalent, maybe G equivalentization. But it's the category of fixed points under the action. So the objects in this new category are objects in C that are fixed under the action. But what that means that rho G of X is isomorphic to X for all G. Maybe let's say, because remember rho G is an automorphism, so it makes sense that I can evaluate on this, and this will be isomorphic to X. For that, I will need a family of natural isomorphisms. So being a fixed point is X plus a family of natural isomorphisms that need to satisfy a lot of stuff. Okay? And then the maps are just maps that commute with these mu's that I have for each thing. But the idea is that saying that it's a fixed point is a little bit more involved, but it's what you imagine. You would like equality in categories, we don't like equality, so we do natural isomorphism that behave nice. Okay? So this is again a fusion category. Get rid of this. And something that happens that I didn't write there is that the resulting category ends up having inside rep G as a fusion subcategory. Why? Because if you take the subcategory back and you equivalentize, you will get rep G. So that's nice in part because then we can do some other things. So actually there is an inverse construction which is called deequivalentization. And it's again related to this idea that I said in the modularization. And these are inverse constructions. So you have rep G inside the category. Then you can take here this, which will be, maybe I will write this. I don't know how to write this in a nice way. Maybe CA. Okay, maybe it's not transparent anyway. So this K to the G for me are just the algebra of functions on G. And again, what I'm taking are modules in C. So this is an algebra in C. And I take the modules in C of that algebra. And I get the inverse construction. Matt?
I just wanted to ask, it's not the case that all non-degenerate braided fusion 2 categories, sorry, braided fusion 1 categories come from modularization, right? Like, this only produces some of the non-degenerate braided fusion categories, is that right?
Let me think. So basically you have, so in some sense sometimes Dimitri and them, or Nikshik and all of them, like say they think that if you study braided fusion categories, then you can study all the others because you dequarantize and you get basically non-degenerate or slightly degenerate, the ones that have Mueller center Beck or super Beck. That's it, but you want to know if I started with a braided, a modular cut or a non-degenerate one, if it comes from some modularization.
Yeah, because the one on the right also has a G graded, right?
When you started with something braided, you will get something G-crossed.
Right.
But it will be honestly braided also.
It's just that I was just wondering, like, I don't think it's the case that you get all non-degenerate.
The thing is that you need to find some G that you want equivalentize. I need to think if you, if sensible G. In that case, I don't know if you can always have E, the trivial group, but that doesn't.
Maybe in a slightly trivial way, if you're already non-degenerate, then your Z2 is rep of the trivial group. Well, you can modularize that and get yourself.
Yeah, that's what I'm saying. It's like the trivial group, but you want to know if all of them come from a more interesting group. I would need to think. You always have the trivial group, but that's not a very satisfying answer. I guess. I would think if because you will need to find which group to use unless you use the trivial one, right? Yeah, I'm not sure. So one point is that these are inverse constructions. This can be doing a more general setting, but when you started with something braided here and you dequarantize, you will get G-crossed and back. G-cross braiding, which I didn't define, but I mentioned yesterday that were important. Yesterday I also didn't say something. Maybe let me just say quickly. A lot of the things that I said here, at least some of these things, are also known for supermodular categories. So if you're interested in super things, a lot of things are parallel. You need to adjust, but I didn't have time and I forgot to mention. So maybe, let me do a small, not small, but I wanted to introduce a construction, but before let's do extension theory. So yesterday when I defined nilpotent, I used this word extension. Maybe it was not the more easy way to define nilpotency. Maybe it was not that natural because it's easier to think in this way with the chain. But extensions play a very important role and actually have been studied in many ways. And then in 2010, maybe or 9, I think of Nikshik and Ostrek developed this extension theory that has been very powerful. So I wanted to mention a little bit. So again, what is an extension? So C tilde is an extension, G extension of C if, again, C tilde will be something graded by the group. So here what I'm doing is I have my fusion category and I'm partitioning in blocks. So these are as abelian things. So I'm putting my simples basically in different blocks, and this is my simple case. But I want this partition to play well with the tensor product. And being an extension of C means that the trivial component is my original category. If you look at only this, a lot of time or all the time we say C tilde is G graded. It's a grading on this. Here we say extension because we're thinking that the smaller category is embedded in a bigger one. And for being an extension, I want all these components to be non-trivial. Basically, what I want is that really this group G is grading my category, not a smaller one. I want all the components to have a sensitive relation with G. So for example, remember yesterday I told you about Tanbari-Yamagami, and we said who are the simples here. The simples here were the group G, or maybe A, because I told you it need to be abelian, and an extra non-invertible. So these are the invertibles, abelian group here, and one non-invertible. And I told you the fusion rules of these were X tensor X is the sum of the group elements, and all the group elements fixed X. So we can decompose our Tanbari-Yamagami as as C till maybe as Tanbari-Yamagami 0 plus Tanbari-Yamagami 1, in which here we'll put A, the simples in A, and here I put X. I mean, I should tell you a little bit more about this, and I will say in a second, but I will not justify everything. And this is a good grading, because if you tensor something here with something here, you stay here, which is what you wanted, and something here times here, you get here. So this is a set 2 grading. So Tanbari-Yamagami is set 2 grading. And if you think about it, the only gradings that admits are set 2 or E, or the trivial grading, not other gradings. The other near group categories that I told you about, and I said, oh, this is very different, the M different from 0 has some advantage or disadvantage, or the M equals 0, which is Tanbari-Yamagami, has some advantages, is because in the other grading, in the near groups, the M here makes that you cannot split these two things. Where X is, all the A's need to be also, and then it's only trivially graded. The near groups that are not Tanbari-Yamagami doesn't accept any other non-trivial grading. Yes.
Is there any work on graded extensions by maybe like a fusion ring or something? Because maybe these other Tanbari-Yamagami or like these other near group things.
You want to grade by something that it's not a group.
Yeah.
Some people think about this. There is some work by Marcel Bischoff and things. The thing is that here, if you add the, I mean, I will delete it because this is not Tanbari-Yamagami, this, then all this will need to be in the same component. There is no way. You will need to have all together. I mean, maybe if you change some definition, it will work, but these all go together because they are the result of something. But maybe if you change what you want to do, the tensor product is fine. But in principle, for this definition, these are the set 2 graded, and the others are all only trivially graded. And here, this category ends up being Vec A. So this is a pointed category. All the simples there are invertible. For some reasons, that basically here I have only one element, means that this will admit some fiber factor, so I will need to have really a Hopf algebra. I cannot have the omega there. But in any case, what I wanted to say, Tanbari-Yamagami is an example of a set 2 extension of Vec A. Okay? That's one example. Also, Vec G omega is an extension, a G extension of Vec. Okay? So these are some examples of extensions. But it would be nice, I mean, it's a nice idea, but we want to know when the extensions exist, are there abstractions, how we construct them. So, in this paper that I was mentioned, that it's called Fusion Categories and Homotopy Theory, they work on this. And there are follow-up papers on these kind of things. So this paper is by Etinovnik and Ostrich, and they work this case and some G-crossed case too. But then Davidov and Nikšić also work on a braided case. So the idea is that if you have this, if you have the extension, And I didn't explain these words, to be honest, but we will think that these are categorifications or notions that we know for rings. So the idea is that if we have this, if you think about this component, when you do the tensor product here, we end up here, right? So basically, it's like if we can think that there is an action of this, our original category, the C, the trivial component, on CG. In this case, I'm acting just by the tensor product. The thing is that I have this kind of, there is a notion of a module category over a fusion category. Like you have modules over rings, right? Fusion categories are categorification of rings, and this will be the other categorification. So you have this, and you also have it in the other direction. Maybe this is not the nice way to get it, but you have it in both directions. So basically, what we're saying, and I will not define module categories, but or by module category, but it's what you would imagine if you want to write the definition of what would be categorified is. So the graded components are CE by module categories. They need to be CI by module categories. But because this is a grading by a group, moreover, when you do this, CG, I'm losing the tilde, sorry. You have an inverse. And when you do this, or the other side also, you lie in the trivial component. And again, I'm sorry that I will black box a lot of things, but the idea is that when you have two bimodule categories, as when you have bimodules over rings, and the rings in the, like, if this is a bimodule in the right by something and this is a bimodule in the left by something, you can take a product of them by killing, like putting together the two actions by the same category. And in principle, you get something new. In this case, you get a bimodule with the actions here. This thing here is telling you that this product of the bimodules will be the trivial or your original thing. So what basically is saying is that there is some invertibility going on here. So these are actually invertible bimodules. And if this doesn't make that much sense, it's okay. But the idea is that we can have this important collection of bimodules, and they will have a nice structure. So here what we will do, this is our original category. This was the input that we had. The input that we had was G and C, and we want to do the extensions. If I want to construct extensions, I need to know who are the invertible bimodules of C. So this will be the invertible bimodules of C. And I'm being very sloppy here. I mean, you need to write something better. You can define it higher with more structure. I'm just saying it very briefly. And then if I want to define an extension, I will need to have a map from G to this Brouwer-Picard group of C. This is the name Brouwer-Picard, that send each of these to one of these invertible bimodules. But of course, life is not that easy. If I do that, yeah, I will have a grading, but that doesn't mean that I will get a nice fusion category. So there are a couple of things that you can do. Okay, I don't know if this is the best, but so in this paper, I think of Nixik and Ostrich prove that this is equivalent to the tensor autoequivalence of the center of our category. So again, this center is very important. If you are not familiar, I do encourage you to look at it. It's important. So you can encode this using this. Sometimes this is more approachable, sometimes this one, depending on the case. And if you see now, it's like similar to things that we have seen before. So basically, to be able to have an extension, I will need this map be more like an action. I would like something more like an action, because I would like some compatibility when I want to do the tensor products. So there will be obstructions for this extension to exist. First, I want this map, but even if I have a map like this, that I would like this to be a group homomorphism in order to respect this part, at least I want a group homomorphism, right? From here. Okay, so from here, I want my original map, this map, to be a group homomorphism. So at least I will get something that satisfies these things. But then to have coherent fusion rules and associativity, this map here needs to be upgraded to a higher map. I told you that when I was looking here for the action somewhere, I was thinking of G as a category, and you can go higher, and you will need to go 2 levels higher for the extension to exist. So extensions are not always possible. There are obstructions, and these are homological obstructions. So these are obstructions that we call 3 and 4, or they call 3 and 4, and they live in and I will write here invertibles of C, maybe center of C because I'm in the fusion case, and here A4 GKX, or C, or the complex there if you want. This one, again, will be more related to have certain actions, so it might be easier to think in this side. But then this one is for associativity to be coherent. So a lot of the time, if we already have a categorical action, we can start with that and try to check if the other obstruction vanish. There is a similar story, but since I haven't defined it yet, and we will see how I do on time, there is a similar story if here I want a G-crossed extension, and I start with a modular category C, or a non-degenerate. If I start with a non-degenerate category C, and I want a G-cross extension, you can do something similar. But one of the differences is that because my original category will have a braiding, like think about commutative rings. If you have a commutative ring, every module is a bimodule using the commutativity. So now I have a commutative, a braided category. So every module can be turned into a bimodules, and that are the ones that I will like for my crossed extension. So there is a similar theory, and instead of Brouwer-Picard, it's called Picard group, and it's using these module things. And that's also very useful because the output is G-crossed, so comes with an action for free. But I didn't talk about G-cross yet, but in case it rings a bell, that's maybe useful. So this extension theory is very, very fruitful. For example, these Jordan-Larson categories that I was mentioning yesterday, which are kind of a generalization like this, it's here, of Tamari-Yamagami. Basically, instead of have a set 2 graded, you have a set P graded with P prime, and so you add some things. But they are still extension of Beck A for some special A that they define there. So what they did is they found, they thought of a fusion ring that looked like an extension, and they used the powerful extension theory to prove when it categorifies to give conditions. And actually, Etinghoff and Nitschik and Ostrich, they prove as an example of their construction. Like the Tamari-Yamagami paper is from the 90s, it's a very nice paper, and they compute associativities by hand. They did the example using this theory in a shorter thing, but of course use a lot of machinery, right? This theory has a lot of advantages because you get a lot of things for free when you're looking at it, but sometimes it's hard computational. When you want to look at an example, it's not always easy because you need to know, for example, the Brouwer-Picard group or the equivalence to get started. Of course, you could look for some extensions and not all the extensions. You can pick something and use it, but sometimes finding them, it's not always easy, especially checking that the obstructions vanish. They have formulas and you need to see if that obstructions vanish. In some of the cases, especially when some of the groups that you are extending or things are well behaved, you know by free that the cohomology is trivial, so the extension has to vanish for free. That's what people has used as a, not as a trick, but as an advantage to be able to define these things. But it's a very, very useful theory. So I wanted to use in two ways this theory, or mention two things follow up this theory. So for modular categories, there is something called gauging that it's related to extension theory. So this gauging was defined in the physics, more in the physics literature by Bartesley, Bonderson, Cheng, and Wang. And then in the math literature, we define it with Sean Sui, Cesar Galindo, and Cheng and Wang also. So the idea for us in this setting was start with a modular category. And we started with a categorical action of here. And now I will need to introduce G-cross, so I will mention a little bit what G-cross is. But the idea is that we wanted to use this extension theory to get a new modular category. But I told you when you do the extension theory starting with a modular category, what you can get is a G-cross category. And in this case, as someone asked me yesterday, it's a G-cross category that has modular in the trivial component. So that's nice because Drinfeld, Nilsvik, and Ostrich proved that if you have an extension and the trivial component is modular and you do an equivalentization, that's modular again, or non-degenerate, but non-degenerate again. So you will get that. So maybe let me say what is G-crossed, braided. So maybe C tilde is G-cross braided. If I can decompose G tilde in this way that I was saying before, it's just graded by G. Here I'm just taking care that the grading behaves nice with the product. But now I also want G acting on C tilde. Let's say that I will act by rho maybe, as I was using before. But now I have an action and I have this, so I want the compatibility. Yes, Matt?
And you always mean that G is faithfully graded, right?
For the definition of G-cross, no. You can define it in general. So to arrive, I think define it in general. But what I will do later when I say a G-cross extension, it will be faithful, because for me extensions will be always faithful.
And maps to Burpick are all faithful, right?
No, yeah. If I use the extension theory, yes. For this definition here, in general, you don't. And some people don't want it faithful for some reason, for the definition. But then if you want to pair it up with extension theory here, you need faithful.
If G is not faithful and then you try to gauge, then you'll get something that's not non-degenerate.
No, because when I gauge, I do an extension. So I do want, yeah, exactly, I do want. But for the definition, yeah, and if you want, you can think about faithful always, and it's fine. It's safe. It's just that this definition, you can use it more in general if you want. So you have the action, and you want the action to be compatible. And I might here make a mistake, hopefully. No, so you want this to be coherent with the grading, so you will land in the conjugation of the component. Depending if your action is right or left, which could happen, you want the inverse in some different way. Hopefully since I'm not saying which side, maybe it's okay. And then why it's called G-cross braided is because you want to have a map so you want to be able to to have a map that interchange things, but you want this to be but you don't need H in one of the sides. So if you see, in principle, this is not a real braid because they live in different components, these two things, right? Sorry, these two, did I say it correctly? No, they don't live in the, I did correctly. So now I can have the isomorphism. Sorry, what I wanted to say is, in principle, since I didn't ask, let me do it with components so it's easy. Since I didn't ask the G to be abelian, in principle these two things don't live in the same component, so I cannot have an honest braiding. One lives in GH and the other in HG. So I will correct that, and I hope I did it, yeah, I did it in the correct order, I think. So now I have things that live in the same component, and I can ask for an isomorphism. Yes or no? So I correct, so now this lives also in CGH, and then I have an isomorphism. So it's not an honest braiding, but it's a cross braiding. So I pay the price of using the action to be able to have this kind of braiding between things. And all these need to satisfy a lot of axioms, which I will not grant, right? A lot of coherence between things. So I have this kind of cross braiding. Actually, this cross braiding and the action are not two extra pieces. One is related to the other. There is a way to encode one in terms of the other. And all this notion of G-cross extension, or the G-cross braid diffusion category, is related to some central extension notion. So some category that has a functor to the center. And that's a way to see that these two are connected. But that maybe doesn't matter. So maybe let me say here that what I was saying before, if now I start with here, where I started, extension theory. Okay, if here C now is non-degenerate, so it's braided, then here instead of looking to Brouwer-Picard, I will look to Brouwer-Picard, and I will look at modules that they are, yeah, I will look just at modules, and then I think that they are invertible using the braiding. Using the braiding. So I just care about modules, but I make them be bimodules using the braided. So I look only to that bimodules of these categories, the ones that are given by the braided, and I look at the invertible ones. And there is a similar theory. But here in this non-degenerate case, you don't care about the center because I didn't say that. But in the non-degenerate case, the center is very nice. Maybe I should have said that. Later I can maybe now I can make a comment. So here I made a couple of comments. I said that if C is braided, B is inside. Okay, C is inside the center. But if C is non-degenerate, the center actually factorizes as C and another copy of C using some different, right? And that's why the Hoff algebra sometimes are called factorizable when they are non-degenerate, and this category sometimes also. But what I mean is when you have a non-degenerate category, you don't need to look at the center because all the information is already in the category, so you don't need the center in that case at all. But the extension theory is similar. The difference is that the output, it will be G-cross extension. So it will not be just a grading, it will be equipped with an action and a half grading. Why that's useful for this setting? Because this gauging that we defined, so maybe this was an interlude, it's a two-step process. So step one is a G-crossed extension of we call it C. So we get something that we call this. I don't know if this is a good notation, but it was hard to find a notation. basically it's a G-cross extension of this using ENO theory. Sometimes there might be obstructions. One thing that I also didn't say is this extension theory has the homological obstructions, but the answer, this output, the extension, is not unique. There are torsors. So once you have an extension, one of these that you construct, fixing the fusion rules, the possible associativities are a torsor by homology, meaning that if you give me one of the associativities for a fixed, so if I have an extension with certain fusion rules and certain associativity, all the other extensions with the same fusion rules are these, the associativities are this one times some cocycle multiplying it. It's control the associativity, it's just multiplying by a cocycle after I fix the fusion rules. I don't know if that's clear, but what I mean, it's not unique, the result. You have many of them.
It correspond to the bicharacter in the Tambara-Yamagami standard construction?
Yes, that's a, I mean, you have two data, but yeah, the character.
Yeah, of course they do.
And the sign. Exactly, that's why you have more than one Tambayamagami, because you can, the fusion rules in Tambayamagami, you can never change it, so that's a good example. You get the extension, the fusion rules are fixed, and one will be a multiple of, like, the associativities are given by multiplying with these things. So now we use, in this step, extension theory. So, obstructions, we cannot always gauge, and in principle, multiple outputs. I pick one of them, and then I go to step 2. The good thing is that the output is this G cross thing. So I have, in particular, a G action on this CXG, in this thing, in the output. So now I will do step 2, and I will use this action with one of my other constructions that in principle works in general. I have a category with an action, and I can get the fixed points. So the gauging is just that. And again, there are multiple gaugings, as you can see. So these are the G equivalentization of the fixed points under these actions of CXG. That is again non-degenerate. Because this was a faithful grading, it's an extension, and this one was non-degenerate. So the results end up being non-degenerate. When we did it for modular categories. When I described it, I didn't. What we did was unitary, because in particular, a Tinkoff-Nitschik-Nostrik construction is very nice, but in principle, if you want pivotal or spherical, you need to check that if you start with something pivotal and spherical, the extension also preserves that things, or when, or if there are obstructions. But for unitary, it's a little easier, so if you start unitary, you can go unitary modular also here. So actually, it will be unitary modular in our case. Now with the group, we are finishing a paper on the pivotal extension and spherical extension theory, so hopefully it will be soon out, but this was a long time ago in 2015, and we didn't have that, but for unitary it was easy to see that was fine, that was preserved, so we could go to the modular setting. Some comments about that, about this construction, as I said, by extension theory we have obstructions and multiple outputs. Something good is that, for example, the fusion rules of the equivalentization were computed by Natalia and Bursiu in a paper, so you have things to work with, you have some control. But in general, it's not that trivial to do gauging, just because, in my opinion, it's not that trivial to do extension theory in general. So, but it has some theoretical advantages. So there are some things that you like that are preserved. For example, the central charge of this category and this category, the gauging, is the same one. And also, if you're familiar with that, the width equivalence class is also preserved. It's also the same. If not, It doesn't matter in modular categories and fusion categories, there are different equivalence things that we look. I told you sometimes it's too hard to classify up to tensor or ribbon equivalence, so we look others. One is fusion rules or Grothendieck equivalence, other is Morita equivalence, the one that I mentioned yesterday. But as you saw, maybe Morita equivalence can change a lot of things drastically, but still is one way to classify. There is other that it's Witt equivalence. This one preserves Witt equivalence. That's one thing. But many things we don't know about gauging because, again, it's kind of hard. So some things that we would like to know is how is, for example, the modular data after gauging, how it relates with the original modular data. We did it in some examples, but we don't have a formula in general. Or, for example, something that we care about is the braid group representation associated to the modular category in this case. And we also don't know how it changed after gauging, which would be interesting because there are some open conjectures in terms of this, and we don't know. So these are kind of things. Or in non-semi-simple, how much we need to adapt these, or things like this, we are still interested. But again, theoretically, it's good, it's a little bit hard. One other thing that we proved that might be nice is that if this group is a semi-direct product, which sometimes you like because you can decompose something that is non-abelian in terms of abelian groups, and then some of the things get a little easier, and we did some examples with that. You can do gauging sequentially in 2 steps using abelian, well, I mean, not abelian necessarily, but the 2 groups from the semi-direct product. In particular, for some cases, you can use the 2 abelian groups instead of, we did it for S3, so we used the set 3 and the set 2 instead of directly S3, and it's maybe easier to compute some of the steps, okay? And you can see for free that the obstructions vanish in that cases, but not in the bigger case that directly, so in that sense, it does that. So maybe let me see, because I have
One question.
Yes.
If you have a G cross extension, can you also gauge, so do this equivariantization only for a subgroup of that?
But you will not get the modular thing. I mean, you need to see how the action works.
Because at least in physics, people gauge subgroups, right? So how would that translate into this framework?
If you have a subgroup, I mean, I don't exactly know. I should think about how it translates. I mean, as I was saying, for example, in this semi-direct, you can gauge the group separately, and you get something new, but you need to be careful. I mean, if you have a subgroup, you will need to see how the gradings are changing, which you might be able to do. What I'm saying is I don't know how exactly the result will relate with this one. It's not that you cannot do it. You will need to see how the subgroup induce a grading, which you can check, and then how the subgroup induce the action and do a gauging, but it will be a different. Maybe let me say one thing. For example, the dimension of this gauge here just because, since we are here, I will say some things. So the dimension of an extension is the dimension of the trivial component times the order of the group. And the dimension of the equivariantization is the dimension of the category times the order of the group. So the dimension of this is, in these steps, I got the dimension of C times the order of G, and now I got that dimension times the order of G, so you get G squared dimension of C. So you see that you will change. It will not be the same theory, but it will be some other theory that maybe you can relate to the other. And as I said, in the sequential gauging case, we could. But you need to be careful, maybe be a little careful, yes.
Is the central charge an invariant of Morita equivalence class?
I need to think. Quickly, I would say no, but I don't know. I need to think for a second. I don't know. I mean, it's maybe yes, because it centers. You want to break the equivalence. I will think for a second. I mean, the thing is, the central charge you want it for modular, and the centers in the modular categories are basically the category. And it's not, but it's related. So in this, I would say yes for the modular case. But Any other question? Maybe since we're in the time of the coffee break, I will stop here and then I will continue with some other constructions.